There's something that happens to a person late at night when the house has gone quiet and the screens have been turned off and they find themselves standing outside under a sky full of stars. Something shifts, something tightens in the chest, and for just a moment, before the rational mind rushes in to name and explain and dismiss, there is a raw, wordless sensation that feels less like wonder and more like falling. Why does that happen? Why does the universe at its most beautiful feel like the edge of a cliff? Why do those who look hardest at the cosmos feel the most alone? Feynman felt it too. He felt it, and he chased it, and he refused to look away. And what he found when he looked was not reassurance. What he found was something far stranger, far more unsettling, and ultimately far more magnificent than any comfortable story could ever offer. But before we arrive at that, let us start somewhere much smaller. Let us start with water. Mira, water is the most ordinary thing in the world. You drank some this morning, you showered in it, you looked out at a gray sky and felt it pressing down in the form of humidity. Water is so familiar that most people have completely stopped seeing it. They have made the mistake, as Feynman used to describe it, of confusing naming something with knowing it. You learn the word water as a child. You learn the formula H2O somewhere in school, and then you close the file mentally and move on, understood, filed, forgotten. But here's what Feynman would want you to sit with for just a moment. Water is broken, deeply, structurally, beautifully broken. It violates so many of the rules that physics has laid out for orderly, well-behaved matter that if you encountered a substance like water described in a textbook, without knowing what it was, you would assume someone had made an error in the calculations. You would send back the paper. You would say this cannot exist, and yet it does. It is in your blood. It covers most of the planet. It is, in the most literal sense, the reason you are alive to be confused by it. And that, Feynman would say, is the beginning of real science. Not the comfortable stories, the cracks in the comfortable stories. Pews, before we go any deeper into what water actually does and why it refuses to behave, let us establish something about the world you're standing in, because the question of water is not merely a chemistry question. It is a question about what kind of universe this is. It is a question about how often the rules get bent, and what it costs when they do, and what it means for the enormous, terrifying silence that greets us every time we point our best telescopes at the sky and listen for. Neighbors, you know the feeling. You have had it even if you have never put words to it. You're going about your day, ordinary tasks, ordinary thoughts, and then something small and strange intrudes, a documentary, a headline, a conversation where someone mentions that there are more stars in the observable universe than grains of sand on every beach on Earth, and suddenly the ground feels slightly less solid. Suddenly the walls of your house feel slightly theatrical. Because if there are that many stars, and if even a tiny fraction of them have planets, and if even a vanishingly small fraction of those planets have conditions anything like ours, then the numbers insist that the universe should be loud with life, busy, crowded, radiant with signals from 10,000 civilizations, all trying to understand their own water and their own stars. And instead, there is silence. That silence has a name. It is called the Fermi paradox, after the physicist Enrico Fermi, who, during a lunch conversation in the summer of 1950, turned to his colleagues at Los Alamos and asked, with characteristic directness, where is everybody? The numbers demand neighbors? The sky offers nothing. Why do those who look hardest at the cosmos feel the most alone? Now, if you have ever heard someone try to dismiss that question, wave it away with a casual remark about how space is very big and maybe they just have not found us yet, then you have encountered what Feynman spent a great deal of his career fighting against. He called it the disease of false comfort. It is the intellectual equivalent of closing your eyes during the scary part of the film and telling yourself nothing is there. Here's what the dismissal misses. The Milky Way is roughly 100,000 light years across. A civilization that develops even modest space travel capabilities, nothing science fiction, just slow, persistent expansion, could colonize the entire galaxy in perhaps 10 million years. That sounds enormous until you remember that the galaxy is over 10 billion years old. 10 million years is 1/10 of 1% of the galaxy's age. In cosmic terms, any civilization that got a head start of even a few 100 million years on us should have filled the entire galaxy so thoroughly, so completely, that we would find their fingerprints on every planet. their signals saturating every frequency, their presence unmistakable, and we find nothing. Nothing at all. That is not a minor puzzle. That is a screaming, howling, existentially terrifying absence. And before you click away, before you tell yourself this is too heavy, or too strange, or too far from your daily concerns, consider this. The answer to Fermi's question, whatever it is, has direct implications for your life, for the life of everyone you have ever loved, for the probability that the civilization you belong to survives the next 500 years. This is not abstract. This is the most urgent question in the history of our species. If you do not understand the shape of this mystery, you're navigating your existence without the most important map. Stay, because it gets stranger, and the strangeness starts, of all places, with water. Now, if this kind of deep sky thinking, where physics and philosophy and the sheer vertiginous scale of the cosmos collide in a single breathtaking question, if this is the kind of thinking that makes your mind feel alive, then consider joining the crew. Subscribe, leave a comment below telling us, do you think the silence of the universe is a warning? Or do you think we are simply the first? Be specific, be honest, because the conversation in the comments below these kinds of videos is genuinely one of the best places on the internet to find other minds that have not gone numb to the wonder. The crew is assembling. Get on board. Now, back to the water. Fíjate bien, when Feynman taught, he had this habit of beginning with something that everyone thought they understood, and then very carefully, very precisely removing the floor. And water is a perfect subject for that treatment, because water is a substance that most people carry around in their heads as a solved problem. We know water, we drink water, and so the strangeness of it has been completely bleached out by familiarity. So let us put the familiarity aside and look at what water actually does. The first strange thing is that water expands when it freezes. This sounds mild. It does not feel like a violation of deep physical law until you compare it to almost every other substance that has ever been studied. Nearly everything, when it cools, gets denser. The molecules slow down, pack together more tightly, and the solid form sinks to the bottom of the liquid form. Iron does this. Alcohol does this. Nearly all molecular compounds do this. It is what you would predict from first principles if someone described a molecule cooling through its phase transitions. The solid should be denser. The solid should sink. Water does the opposite. Ice floats. Why? Because of the specific geometry of the water molecule and the peculiar behavior of hydrogen bonds. When water freezes, the hydrogen bonds between molecules force them into a crystalline lattice that is actually more spacious, more spread out than the liquid arrangement. The solid form is less dense than the liquid. Ice floats on water. Now pause and feel the weight of this for a moment, because this is not a curiosity. This is the reason life exists on Earth. If ice sank, every winter lakes and oceans would freeze from the bottom up. The ice layer would form at the base, and instead of acting as an insulating surface that protects the liquid water underneath, it would keep building upward, and the surface water would be exposed to the cold and freeze in turn. And this process would continue until the entire body of water was solid. No liquid refuges below the ice. No protected zones where life could persist through the winter. The Earth's water bodies would be death traps every time the temperature dropped. And in the early history of the planet, when ice ages were frequent and extreme, the whole planet could have locked into a permanent snowball state. Frozen, sterile, silent. Ice floating is not a nice bonus feature. It is a critical safeguard built into the physics of a single molecule, and no one designed it, no one engineered it. The shape of the water molecule and the angle between its hydrogen and oxygen atoms, specifically the angle of 104.5 degrees, an angle that looks almost arbitrary from outside, produces this insulating property as a consequence. The universe bent a rule and life survived, but that is not all. Not even close. Bueno, water has an absurdly high specific heat capacity. What this means is that water requires an enormous amount of energy to change its temperature compared to most other substances. You can pour heat into water and it resists changing. You can drain heat from water and it resists changing. It acts as a thermal buffer, a regulator, a shock absorber for temperature. Because of this, the oceans moderate the climate of the entire planet. They absorb heat in the summer and release it in the winter. They keep coastal regions from swinging between lethal extremes. They make the global temperature something that complex biochemistry can survive in. If water had a normal specific heat like most liquids do, the Earth's surface temperature would swing by hundreds of degrees between day and night. The equator would be an inferno. The poles would be colder than anything we can currently imagine. And the narrow band of temperatures in which proteins fold correctly and enzymes catalyze reactions and DNA replicates faithfully would be visited only briefly. In specific locations at specific moments, never long, enough for life to take hold and stabilize. Me Sigs, water's stubbornness about temperature is not a trivial chemical property. It is the reason the stage is set at all. And then there's the surface tension. Water molecules are unusually attracted to each other. The same hydrogen bonding that makes ice float and gives water its thermal stubbornness also makes the surface of water behave almost like a skin. Strong enough that small insects can walk across it. Strong enough that water climbs up narrow tubes against gravity in a process called capillary action, which is how trees pull water from their roots to their highest leaves, hundreds of feet in the air without any pump, without any engine, purely through the geometry of molecular attraction and the anomalous stickiness of water molecules. Without capillary action, tall plants could not exist. Without tall plants, the atmosphere would have a different composition. Without that atmosphere, the creatures that evolved to breathe, it would not exist. And the chain of consequences unravels back to a single molecular angle in a single molecule. Here's where Feynman would lean forward and say something that sounds simple, but is actually one of the deepest observations in all of science. He would say, when you look at something this specific, this precisely calibrated, this full of consequences that happen to point in the direction of complexity in life, you have two choices. You can say it was engineered, or you can say that in a universe as vast as this one. The instances where the rules bend in exactly this way are the instances where you find something capable of noticing that the rules bend. Every other configuration, every universe where water behaves normally, and ice sinks and oceans freeze, produces no one to write the equation and no one to feel the wonder. This is the anthropic principle, and Feynman approached it with characteristic caution. He did not use it as an excuse to stop asking questions. He used it as a reminder that our sample of one is deeply structurally biased. We are here precisely because here's the kind of place where the rules bent enough to allow here to happen. And this is where the chill returns. This is where the Fermi paradox comes crashing back in through the window. If the rules can bend like this, if water can be this anomalous, if the conditions for life are this, achievable through pure physical coincidence, then the universe should be overflowing with places where the same bending occurred. The numbers still demand neighbors. The silence is still deafening, and the implications of that silence are, if anything, made worse by knowing how generously the laws of physics seem to bend toward life. Why do those who look hardest at the cosmos feel the most alone? Let us go deeper, because we have only talked about the anomalies of water itself, and there is an entire second layer of strangeness waiting just beneath the surface. Water is called the universal solvent. This is not marketing language. It is a description of an almost shocking chemical promiscuity. Water dissolves more substances than virtually any other liquid. It does this because the water molecule is polar, meaning one end of it carries a slight positive charge and the other end carries a slight negative charge, and this polarity lets it reach out and grab ionic and polar molecules and pull them apart and surround them and carry them in solution. Salt dissolves in water not because water is aggressive, but because water is relentlessly social. It wraps itself around every available ion and refuses to let go. What this means for biology is profound. Every chemical reaction that happens inside a living cell happens in water. The nutrients that enter the cell arrive dissolved in water. The waste products leave dissolved in water. The enzymes that catalyze the reactions are proteins that fold into specific shapes in a water environment, and the water molecules themselves participate in the folding, in the catalysis, in the signaling. Life does not happen in water the way a fish happens to live in a pond. Life happens through water the way a symphony happens through air. The medium is not passive. The medium is part of the instrument. And yet, despite all of this, despite the extraordinary specificity of water's anomalies, despite the way they stack together into a coherent life-enabling system, water is made of two of the most common elements in the universe. Hydrogen is the most abundant element that exists, Born in the first minutes after the Big Bang, oxygen is produced in massive stars and scattered across the galaxy by supernova explosions. Wherever there are stars, there is the raw material for water. The molecule that breaks the rules, the molecule that made us possible, is assembled from ingredients that the cosmos manufactures in incomprehensible quantities and distributes everywhere. Imaginate pour un momento. You're standing at the edge of the Milky Way, looking in 100 billion stars. Most of them have planets. Many of those planets orbit in zones where liquid water is possible. The raw materials for water are everywhere. The conditions for water are common. The anomalies of water that enable complexity and life are not local quirks. They follow from the laws of physics that apply everywhere in the universe. Wherever water exists in liquid form for long enough, it does the same insulating, regulating, dissolving, capillary climbing, rule-breaking things it does here. The universe should be screaming with life, and yet, pews, this is where we must talk seriously about what the silence might mean, because there are not many options, and none of them are comfortable. The first option is that life is extraordinarily rare in ways we do not yet understand. That despite the abundance of water and the right temperatures and the right chemistry, there is some additional step, some crossing from non-living chemistry to living, self-replicating, metabolizing chemistry that is so improbable that it has happened only once or perhaps only a handful of times in the entire observable universe. We call this the rare Earth hypothesis, and it is not obviously wrong. We have exactly one example of life arising. One, our sample size is catastrophically small. The transition from chemistry to biology may require a coincidence so extraordinary that it makes water's anomalies look routine. We do not know. The second option is that life arises readily, but something kills it. This is the great filter. Idea first articulated by economist Robin Hanson in the 1990s is that somewhere on the path from simple chemistry to a civilization capable of colonizing galaxies, there is a filter, a barrier, a bottleneck so severe that virtually nothing passes through it. A point at which the vast majority of would-be civilizations are stopped, exterminated, or destroyed. And the critical question, the question that should make your hands go slightly cold, is whether that filter is behind us or ahead of us. If the filter is behind us, if the nearly impossible step was the origin of life itself, or the development of the eukaryotic cell, or the emergence of complex multicellular organisms, then we got lucky. We are the survivors of an almost impossible gauntlet, and the silence of the universe is explained. Nothing else made it through. We are alone, but we are alive, and the future, if we are careful, is open. If the filter is ahead of us, the universe looks very different. It means that civilizations regularly reach something like our current stage of development, and then they fail. They destroy themselves. They are destroyed by something external. They hit a wall that we in our current state of understanding and self-governance and technological hubris cannot see. And here's the piece of information that should make you stop whatever you're doing and think. The discovery of life elsewhere in the universe, particularly complex life, would be at first glance wonderful news. Evidence that we are not alone, evidence that the universe is teeming, but think it through. Think it through the way Feynman would insist you think it through. If we find life on Mars or in the oceans of Europa, or in the chemical signatures of a distant exoplanet's atmosphere, it means the origin of life is easy. It means that step is not the filter, and if the origin of life is not the filter, then the filter must be somewhere else, somewhere further along the path, somewhere we have not yet reached, closer to where we are. The more life we find, the more terrifying the silence of advanced civilizations becomes. Why do those who look hardest at the cosmos feel the most alone? Because the harder you look, the more you understand that the question is not just poetic, it is a diagnostic. The silence is data. And what it might be telling us about the life expectancy of intelligent civilizations is the most important information we have ever failed to receive. Bueno, let us come back to the water for a moment, because there's one more anomaly that Feynman would want to hold up to the light, and it connects everything we have been building toward. Water is a liquid at room temperature. This sounds obvious until you compare it to its chemical relatives. Water is composed of oxygen and hydrogen. If you look at the other molecules formed by hydrogen and an element from the same column of the periodic table as oxygen, specifically hydrogen sulfide, hydrogen selenide, and hydrogen telluride, you find that they are all gases at room temperature. In fact, if you extrapolate from the trend of those molecules to predict when water should boil, simple extrapolation tells you that water should be a gas at anything above roughly minus 80 degrees Celsius. By the logic of its family, water should be a gas at every temperature that exists on the surface of the Earth. There should be no liquid water here. There should be no oceans. The hydrogen bonds are what change the math. The same molecular stickiness that makes ice float and gives water its thermal stubbornness also raises the boiling point of water by something like 160 degrees compared to what physics would naively predict. That is not a small correction. That is a miracle of molecular architecture achieved without any architect. Low V's, every one of water's anomalies, the floating ice, the high specific heat, the extraordinary surface tension, the universal solvent behavior, the improbably high boiling point, all of them trace back to the same source. The angle between the hydrogen and oxygen atoms in the molecule and the resulting hydrogen bonds. One geometric feature, one precise angle, and from that single fact, the entire apparatus of life-enabling chemistry unfolds. Feynman would say that is what physics looks like when you actually go all the way down. You find that the universe is built from astonishingly simple rules that generate astonishingly complex consequences. And the moment you truly understand that, you cannot go back to seeing the world as flat. Now, here's the question that bridges the anomalies of water and the silence of the cosmos. And it is a question that science has only recently begun to formulate clearly. If the rules of physics are universal, and we have very good reason to believe they are, then the same rules that produce water's anomalies on Earth produce them everywhere water exists. The same angle between hydrogen and oxygen that makes ice float here makes it float on an ice moon orbiting a distant gas giant. The same hydrogen bonds that keep Earth's oceans liquid at room temperature keep other oceans liquid on other worlds. The physical laws are not local. They are the same everywhere, at every time, in every corner of the observable universe. This is one of the most profound and underappreciated facts in all of science, and Feynman considered it close to miraculous in its implications. So the life-enabling properties of water are not something that had to be specifically arranged here on this planet for us. They are consequences of the fundamental laws that govern all matter everywhere. And this means the universe has built into its most basic operating system the instructions for making a molecule that insulates lakes, regulates climates, dissolves chemistry, and enables biology. Not just here, everywhere. The universe seems almost eager to make life possible, and yet the silence persists. Tina Santito? The gap between the eagerness of the physics and the emptiness of the sky is the most disturbing thing in modern science. It suggests either that something we do not understand intervenes between the conditions for life and the development of civilizations, or that something we do not understand destroys civilizations before they can make themselves known. A Tuesday in October several decades ago, a group of scientists gathered at the Green Bank Observatory in West Virginia for the first scientific conference ever held on the search for extraterrestrial intelligence. There were 10 people in the room. Feynman was not among them, but the spirit of what he represented. The insistence on following the evidence without blinking, without flinching, even when the evidence was uncomfortable, that spirit was very much present. The conference produced something called the Drake equation, a systematic way of estimating how many communicating civilizations might exist in the galaxy at any given time. It is not a formula that produces a precise number. It is a way of organizing ignorance, which is, as any honest scientist will tell you, exactly what the best early science looks like. You name the things you do not know in a precise enough way that when you eventually learn them, you can update the answer. The Drake equation has factors for the rate of star formation, the fraction of stars with planets, the fraction of those planets in habitable zones, the fraction where life actually arises, the fraction where intelligence develops, the fraction where communication technology develops, and the average lifespan of such a civilization. Most of the early factors we now know fairly well. Planets are common, habitable zones are common, The later factors remain deeply uncertain. And it is the very last factor, the average lifespan of a technological civilization, that may be the hinge on which the entire question turns. If the great filter is ahead of us, then that last factor is very small. Civilizations tend to be brief, and the reason might be anything. It might be that civilizations inevitably develop weapons capable of destroying themselves before they develop the wisdom to refrain from using them. It might be that industrial technology inevitably produces environmental changes that destabilize the conditions that supported life. It might be something external, a gamma-ray burst, a nearby supernova, an asteroid impact that civilization-level technology did not develop fast enough to deflect. It might be something we have not imagined yet, or it might be something subtler and more insidious. It might be the death of curiosity. This is where Feynman's voice gets very quiet and very serious. He talked about this in different ways throughout his life, about the danger of a society that stops asking questions, that mistakes the comfort of familiar answers for actual knowledge, that learns to perform understanding rather than pursue it. He saw it in pseudoscience and in rigid dogma and in the easy satisfaction of slogans. He called it at various times cargo cult science because it had the superficial appearance of the thing without the substance. And he believed with a passion that was almost physical that it was a kind of civilizational disease. Myra, a civilization that stops being curious about the actual nature of reality, is a civilization that stops being able to respond to reality. It begins to mistake its own models for the territory. It doubles down on comfortable stories in the face of disconfirming evidence. And in a cosmos where the challenges are real, where the asteroid impacts are real, where the climate feedbacks are real, where the probability of self-destruction is real, a civilization that has abandoned the tools of genuine inquiry is a civilization that has begun its approach to the filter. Why do those who look hardest at the cosmos feel the most alone? Perhaps because looking hard enough to see both the beauty and the danger is uncomfortable, and discomfort drives most people back to the comfortable stories. And so the ones who stay and look are always, by definition, a small and slightly lonely group. But let us not end in despair, because this is where Feynman, even at his most unsettling, always turned the corner. He did not believe in despair as a final answer because despair is a story you tell yourself when you have stopped asking questions, and Feynman never stopped asking questions. Fait bien, here's what the anomalies of water actually teach us, properly understood as a tool for thinking about the cosmos. Every one of water's rule-breaking properties emerge from the consequences of simple universal laws. Nobody designed the hydrogen bond angle. Nobody engineered the specific heat. Nobody arranged for ice to float. These properties emerge from the mathematics that governs the interaction of electrons and protons, the same mathematics that governs the stars and the galaxies and everything in between. They are emergent. Complexity emerging from simplicity, order emerging from rules that know nothing of order. This is one of the most important ideas in science, and Feynman believed it was vastly underappreciated by the general public. Most people, when they think about the universe, assume that complexity requires a complex source, that a complicated world implies a complicated origin. But physics says something different. Physics says that the rules can be extraordinarily simple and the consequences can be extraordinarily rich. A single equation, the Schrödinger equation, contains in principle every chemical behavior of every molecule that has ever existed, including the angle of the water molecule, including the hydrogen bonds, including the insulation of ice and the moderation of climate and the capillary action in trees and the solvent behavior that makes your blood work. All of it falls out of a single equation. That is not a simplification or a metaphor. That is precisely what the equation does. And what this tells us about the silence of the universe is something both humbling and strangely hopeful. It tells us that the universe is not arbitrary. It has rules. Those rules are knowable. And the more completely we know them, the more accurately we can predict where life should be, how it should behave, what threats it faces, and what tools it has available to survive those threats. The search for extraterrestrial intelligence is, at its core, an exercise in applying those rules at cosmic scale. It is asking, given what we know about physics and chemistry and the emergence of complexity, where else in this enormous, ancient, star-filled universe have the conditions been met? And the silence we hear back is not the end of the inquiry. It is the next question. Let us get specific about some of the candidate answers, because Feynman would insist on specificity. Vague existential dread is not a scientific position. The first candidate is the hypothesis that technological civilizations are self-terminating on a timescale of centuries. This is perhaps the most sobering possibility because it implies that the filter is something civilizations bring on themselves. The development of nuclear weapons, the disruption of climate systems that evolution optimized for over millions of years, the creation of artificial intelligence systems that behave in ways their creators cannot fully predict. All of these represent inflection points at which the consequences of civilization's own tools could become existential. We are not the first civilization to face such inflection points if the Great Filter hypothesis is correct. We are simply the most recent candidate for the filter. The second candidate is the possibility that civilizations deliberately go silent, choosing not to broadcast their presence in a universe where announcing yourself might be dangerous. If one civilization used broadcasting to attract the attention of a predatory or competitive civilization, the evolutionary pressure on all subsequent civilizations would be towards silence. This is called the dark forest hypothesis, after a metaphor in which the universe is a dark forest full of hunters, each one silent, each one listening, each one aware that any sound might bring a bullet. If this is true, the silence is not an absence of life, it is the sound of life hiding. The third candidate is the zoo hypothesis, which is frankly the most uncomfortable one to think about for too long. It proposes that advanced civilizations exist and are aware of us and have made a deliberate choice not to make contact, either because they are observing us as we observe animals in a reserve, or because there is some kind of prime directive in operation, some agreement among advanced civilizations not to interfere with developing ones. Under this hypothesis, the silence is artificial. It is maintained. We are watched and we do not know it. Feynman would probably say that the zoo hypothesis, while technically unfalsifiable, has a certain uncomfortable elegance to it. He would probably also note that it is the hypothesis that most people secretly find both most frightening and most consoling, which is a useful data point about human psychology and probably not a very useful data point about the actual universe. What he would insist on is this: the answer we arrive at when we finally understand the Fermi paradox will change everything. Not just our understanding of the cosmos, our understanding of ourselves, our understanding of what we are capable of, what we are risking, and what tools we have to navigate the most dangerous period in our civilization's brief existence. Bueno, let us bring this all the way back to the beginning now, because everything connects. You started in your mind standing under a night sky. You felt that tightening in the chest, that sense of falling that comes from genuine cosmic perspective, and you have just spent the last stretch of this conversation learning why that feeling is not irrational anxiety. It is appropriate calibration. The universe is 13.8 billion years old. The Earth has been hospitable to life for roughly 3.5 billion of those years. Modern humans have existed for perhaps 300,000 years. Industrial civilization, the kind capable of producing radio signals and space telescopes and artificial intelligence, is about 200 years old. 200 years against 13.8 billion. If civilizations typically last 1,000 years, which would be catastrophically brief, we are already 1/5 of the way through ours. If they typically last 1,000,000 years, we are in the very first moments of ours. The uncertainty in that estimate is itself a form of information about how urgent it is to understand the filter. And the water, the rule-breaking anomaly-riddled, life-enabling water is the perfect lens through which to see why understanding the actual laws of physics matters so much. Not physics as a list of facts to be memorized. Physics as a way of seeing. Physics as the tool that lets you look at a molecule with a strange angle and trace its consequences all the way to the survival of complex life on a blue planet in an ordinary spiral galaxy. Feynman had a word for what it felt like to actually see a piece of physics properly. He called it the pleasure, not the satisfaction, not the pride, the pleasure. The physical, almost aesthetic sensation of a real explanation clicking into place. He thought everyone was capable of feeling it. He thought it was being denied to most people by a system of education that confused the names of things for the understanding of things and confused the authority of experts for the process of actually knowing. He was furious about this in the specific way he was furious about things, which was precise and pointed and absolutely without malice. He was not angry at the people who had been denied it. He was angry at the denial. Me Sigs, this matters because the greatest threat to our civilization's survival might not be an asteroid or a supervolcano or even our own weapons. It might be the comfortable closing of the file, the decision to stop looking at the night sky, the assumption that the questions have been answered and the wonder can be set aside. Because a civilization that loses its capacity for genuine wonder loses its capacity for genuine inquiry. And a civilization that loses its capacity for genuine inquiry loses its ability to see the filter coming. The universe does not care whether we survive. It ran the experiment before, with other configurations of matter on other planets orbiting other stars, and if the Great Filter is ahead of us, most of those experiments ended quietly, without fanfare, without a record, without anyone left to ask why. The silence in the sky is, in some interpretations, a graveyard, and the headstones are planets that once had oceans. But here's what Feynman knew, and here's what the anomalies of water demonstrate, and here's the piece of this that should feel not like despair but like a door opening. The universe also contains, built into its most fundamental rules, the conditions for extraordinary complexity. The same laws that allow for gamma-ray bursts also produce the hydrogen bond angle that floats ice. The same physics that can sterilize a planet can also produce 3.5 billion years of continuous biological evolution on a water-covered world. The universe is not hostile to us. It is indifferent. And indifference is not hostility. Indifference means the territory is navigable if you learn to read it. We have the tools. We have the mathematics that runs all the way from the quantum behavior of electrons to the structure of galaxies. We have telescopes that can detect the chemical signatures of atmospheres on planets orbiting stars dozens of light years away. We have a species-level knowledge of our own civilizational vulnerabilities that is unprecedented in the brief history of intelligent life on Earth and possibly unprecedented in the history of the galaxy. We know about the filter. We are one of the first, possibly the first species ever to identify the concept and ask the question deliberately. That is not a small thing, that is staggering. The universe has produced, in at least one location, a collection of atoms that can contemplate the conditions for their own existence and ask whether those conditions are common. Feynman thought this was the most remarkable fact in all of science. More remarkable even than the specific equations, more remarkable than any experimental result. The fact that the universe became conscious of itself here in us in the strange water-dependent, temporarily upright organisms that emerged from 3.5 billion years of molecular trial and error on a rocky planet in an unremarkable arm of a spiral galaxy. Why do those who look hardest at the cosmos feel the most alone? Because they see clearly, because they understand the scale of the silence and the scale of the stakes and the scale of the rarity of what exists here on this planet. This thin film of water and air and life pressed against a ball of rock. And seeing clearly is lonely in a world where most people have decided the sky is just a backdrop. But it is also the beginning of every real advance our species has ever made. Pews, here's what you take away from all of this. Not a list of facts. Feynman hated lists of facts, but a lens, a way of looking. When you see water, really see it? See the floating ice and the regulated climate and the climbing sap and the dissolving chemistry? See the consequences of one molecular angle unfolding into an entire biosphere. See the rule-breaking as a product of rules. See the impossibility becoming inevitable through the logic of emergence. Then you're doing physics. Not the names of things, but the seeing of things. And once you can see water that way, you can start to see the cosmos that way too. Not as a backdrop, not as a source of pleasant photographs, as a vast, ancient, rule-governed, complexity-generating, intermittently life-enabling experiment in which we are not observers but participants, not separate but continuous, not safe by default but alive by a series of improbable and beautiful molecular coincidences that extend back to the first minutes after the Big Bang. The silence in the sky might be a warning. It might be the echo of filters already passed through by beings that never knew what hit them. Or it might be the waiting. The universe might be, as Feynman would almost certainly have said with a slight smile, just getting started. But it will only get started somewhere if somewhere maintains the curiosity to keep asking what it is standing in. To look at the most ordinary substance in the world and refuse to stop at the name. to insist on going all the way down into the angle between the atoms, into the consequences that radiate outward from that angle across 3.5 billion years, and onto a night sky full of stars that may or may not be looking back. Why do those who look hardest at the cosmos feel the most alone? Because they have understood something that changes the texture of every moment that follows. And that understanding that transformation is not a burden to put down. It is the thing that makes the water extraordinary and the silence urgent, and the next question the most important thing you can think. It is as Feynman spent his entire magnificent, irreverent, wonder-soaked life insisting the pleasure